All right, this is part 6 of our Unit 1 videos, and we are looking at complex numbers. Now, we've been talking about square roots, and so far we haven't done any square roots of negative numbers, but now we're going to essentially define what the square root of a negative number is. So if I have the square root of -1, that is defined as the imaginary number I. If you go back to the very first video in Unit 1, you'll see a chart where we talked about how all different kinds of numbers relate to one another, and I talked about imaginary numbers there. Now, if I have I is equal to the square root of -1, well, I equaling the square root of -1, if I square both sides of that, then I have I squared, and a square and square root cancel each other out, and that's equal to -1. So if I have an imaginary number and I square it, it becomes a real number. So this is a really interesting property. It's really fascinating that you can have an imaginary number, square it, and it become real. There's also something that we will see in this next example, or in our first example, working with imaginary numbers kind of rotating through this cycle as we raise them to higher powers. So if I have I squared and I multiply both sides by I, okay, well then this becomes I cubed, and because I times I squared is I cubed. And then this becomes equal to -1 times I, which is -I. Okay, so I cubed is equal to -I. If I multiply one more time by I, well, that will become I to the 4th power. And then -I times I, well, we already saw that I times I, or I squared, is equal to -1. And -1 times a negative becomes +1. And now if I multiply by I again, it will cycle through and it'll be equal to I. So I has this property where if I have I, that's equal to the square root of -1. I squared is equal to -1. I cubed is equal to I to the 4th power is equal to 1. And then it continues to cycle through. So if I had I to the 5th power, it would be equal to I. If I had I to the 6th power, it would be equal to this. 7th power, 8th power, 9th power, 10, 11, 12, 13, 14, 15, 16, so on. So we can kind of use that property in evaluating I to higher powers. Now, some of the rules for working with complex or imaginary numbers. Adding and subtracting complex numbers, you add or subtract the real parts with the real parts and the imaginary part with the imaginary part. These are called complex conjugates. If I have A plus BI, the conjugate of that would be A minus BI. So same numbers here, the sign on the A is the same, but the sign in the middle, or the sign on the imaginary number, is opposite. And then the square roots of imaginary numbers. Anytime we have a negative inside a square root, before we can do anything else, we need to rewrite it with an I out front. So we're just going to practice. We're not going to go super deep into complex numbers. They really just stay like a surface level topic. We really only introduce them because we need them for working with polynomials and quadratic equations. So just kind of getting a surface level understanding of them. If I have I to the 23rd power, we want to think, what is the smallest number, or I'm sorry, the largest number below 23 that's divisible by 4? Well, the largest number below 23 divisible by 4 is 20. So I could rewrite this as I to the 20th power times I to the 3rd power using our exponent rules. Well, if this is a multiple of 4, then it's going to have this equivalent here. So I to the 20 is going to be equal to I to the 4th, and it's going to be equal to 1. So we're just essentially evaluating 1 times I cubed, and we already said I cubed is equal to -I. And we could do that with any power here. If we are subtracting imaginary numbers, what we want to do is, like we talked about above, subtracting the imaginary part with the imaginary part and the real part with the real part. So I'm just going to first distribute the subtraction here, and I have 6 minus 8I minus 3I, and then a negative times a negative becomes +1. The real part is 6 and positive 1, so that gives me 7. The imaginary part is negative 8i and negative 3i. That's negative 11i. It's kind of like just combining like terms. Multiplying, we can go ahead and distribute. We have 7i times 2, that's 14i. And then 7i times negative 9i is negative 63i squared. But remember, I squared is equal to negative 1. So negative 1 times negative 63 is positive 63 plus 14i. And again, in standard form would be the real part first and the imaginary part second. The next example, we're going to go ahead and use the box. If you prefer foil, you're welcome to use foil. As I've said in previous videos, I prefer the box. So we have 5 plus 4i, and then we have 6 minus 7i. 5 times 6 is 30. 5 times negative 7i is negative 35i. 4i and 6 is 24i. And 4i and negative 7i is negative 28i squared. But remember, I squared is actually negative 1. So this is really negative 1 times negative 28. So negative 28 times negative 1 is positive 28 plus 30 minus 35i plus 24i. Simplifying that, we have 58 minus 11i. And the next one, we want to divide and express in standard form. And the way we divide complex numbers is similar to rationalizing denominators. So we're going to be multiplying by the complex conjugate of the denominator. So if I have 2 minus 5i, the conjugate of that would be 2 plus 5i. And we'll multiply by that on top and bottom. That means I'm going to need to use either FOIL or the box on top and on bottom. And if you've done this before, you know there's a shortcut for the bottom, but I'll talk about that after. So I'm going to go ahead and do a box for the top real quick. I have 7 plus 4i, and I have 2 plus 5i. It's 14, 35i, 8i, and 20i squared. Well, I squared is negative 1, and negative 1 times 20 is negative 20. Negative 20 and 14 is negative 6. And 8i plus 35i is 43i. On bottom, we can go ahead and do a box for the bottom as well. And like I said, I'm going to show you a shortcut for the bottom. We have 2 minus 5i and 2 plus 5i. It's going to give me 4, negative 10i, positive 10i, and negative 25i squared. I squared is negative 1, so negative 1 times negative 25 is 25. So the real part is 25 plus 4, that's 29. And notice that the imaginary parts cancel out. Positive 10i and negative 10i cancel each other out. So that's the whole process of dividing complex numbers, is we want to get the imaginary portion of it out of the denominator. Now you can leave it together as a single fraction like this, or you can separate it. But if it was possible to write or to reduce this fraction, we would need to reduce them. Okay. All right, so the shortcut I was mentioning is we really don't need to do a box for the bottom. These pieces will always cancel out. So all you really need to do is the first times the first. 2 times 2 is 4. And the last times the last. Negative 5i times positive 5i is negative 25i squared. And then simplifying that, they'll get the 25 and the 4 and get 29. One more on this topic. Here we have some square roots with negatives inside. We will need to simplify them, and before we can start performing any operations or combining like terms, we need to pull the i's out. That always has to be our first step. So the very first thing I'm going to do is rewrite this as I square root 27 plus I square root 48. We've already practiced simplifying square roots quite a bit. 27 is 9 times 3, so I can pull the 9 out and I'll have a 3 on the outside, so 3i square root 3. 48 is 16 times 3, and the square root of 16 is 4, so I'll have a 4 out front, plus 4i square root 3. These are like radicals. They have the I on them. They have the square root 3, and so this is equal to 7i square root 3. If you don't pull out the I first, it's very easy to make mistakes. We'll see that especially in the next example here, where we would be squaring things. So in this next example, I have negative 2 plus the square root of negative 9, and that whole thing being squared. So what I need to do before I can start applying that is I need to simplify this piece here. Well, let's just look at the square root of negative 9. I can pull out the negative and have I square root 9, and the square root of 9 is 3. So this is equal to 3i. There's no square root left. So the first thing I'm going to do is rewrite this as negative 2 plus 3i squared. Well, that means I have negative 2 plus 3i times negative 2 plus 3i. And we just practiced multiplying out two binomials like that. So let's go ahead and do a box real quick. Negative 2 plus 3i, negative 2 plus 3i, 4, negative 6i, and 9i squared. And I squared is negative 1, so this is negative 9. So combining like terms here, I have 4 and negative 9. That gives me negative 5. I have negative 6i and negative 6i. That's negative 12i. And then the last one here, we have a square root with a negative inside. I need to simplify that as much as possible. So remember, square root of negative 12, the first thing I would do is pull the negative out and have an I out front. So negative 14 plus I root 12 over 2. And the square root of 12, well, that's the same thing as the square root of 4 times 3. And we can take the square root of 4, that's 2. So we can rewrite that as negative 14 plus 2i root 3 over 2. Now when we are reducing things like this where we have two terms on top and one term on the bottom, in order to reduce the fraction, it has to reduce with the number in the front of the square root, the number over here, and the bottom. Well, all three of those are divisible by 2, so I could reduce this to negative 7 plus I root 3 over 1, and I really don't need the over 1, so I can leave it just like that. All right, moving on to the next page here. We're going to be looking at solving some equations, and we're going to start out just with some basic linear equations, and I'm going to show you a trick for getting rid of fractions, and then we're going to move on to some other types of equations. So in this example here, notice that I don't have any variables in the denominator. So because it's just numbers in the denominator, what I can do here is I can multiply by the common denominator everywhere. Well, between 4 and 3, the common denominator would be 12. So I'm going to multiply both sides of my equation by 12. And on the right-hand side, that's going to be 24. On the left-hand side, if I have 12 times x plus 2 over 4 and minus 12 times x minus 1 over 3 equals 24. 12 and 4 reduce. That becomes a 3. 12 and 3 reduce. That becomes a 4. And now I have no more fractions. Fractions are gone. I just have 3 times x plus 2 minus 4 times x minus 1 equals 24. From there, I can go ahead and distribute the 3, distribute the 4, and that'll give me 3x plus 6 minus 4x plus 4 equals 24. Kind of running out of space here. So then, combining like terms on the left-hand side, 3x and negative 4x is negative x, and 6 plus 4 is 10 equals 24. Subtracting 10 from both sides, I have negative x is equal to 14, so x is equal to negative 14. And as long as I don't have any variables in the denominator, I don't have to check my answer because there's nothing that would make my denominator 0. There's just numbers there. The next example is solving what's called a literal equation, or solving a formula for a variable. So what we're trying to do here is to solve for a single variable, try to get that variable by itself. So in this case, this big A, this H, this little a, all of those are acting like numbers, and B is acting kind of like our X, like our variable. So I'm trying to break everything off of this side except for the B. Now the first thing I'm going to try and get rid of is this 1/2. And the way I can get rid of a 1/2 times the rest of this is to multiply both sides by 2. So on the left side, I have 2a. On the right-hand side, the 2 and the 1/2 cancel out, and I'm left with h times a plus b. Now, oftentimes what I'll see students do is distribute the h, and that's not wrong. It's just not, in my opinion, the most efficient way to go about this, because you end up doing a step that you end up wanting to undo later on. So I'm going to go ahead, if I have h times a plus b, and I'm trying to get this h off of here, I can divide both sides by h. And now I have 2a over h is equal to a plus b. And the only thing left on this side that I want to get rid of is the a. So I'm going to subtract a from both sides. And I'm left with b by itself. And then 2a over h minus a. And this minus a is just off the end. It's not part of this fraction. This was what's on this side here, and then I subtracted a from that whole piece. Okay. Now we are going to shift gears a bit and talk about solving quadratic equations. And over the rest of this video and the next at least 1 or 2 videos, we're going to look at 4 different methods. We're going to use factoring to solve quadratic equations, so using the X method or whatever method you prefer for factoring. Then we're also going to look at solving quadratic equations by the square root method. And then third, we will be looking at using the method of completing the square. And then lastly, we will be using the quadratic formula. So these all kind of tie together. We're solving the same kinds of equations, but in different ways. And in order to solve these in all of those scenarios, we will be using what's called the zero product property. And what that means is if I have 2 numbers being multiplied and I know the answer is 0, but I don't know what those numbers are, the only way to get an answer of 0 is if either A is equal to 0 or B is equal to 0, or both. And so, if we have something like this where we have x minus 3 and x plus 2 is equal to 0, then either this equals 0 or this equals 0. And if I set x minus 3 equal to 0, and I set x plus 2 equal to 0, and I solve for x here by adding 3 to both sides, then I get x equals 3. If I subtract 2 over here to get x by itself, I get x equals negative 2. And so that's the property we're using here. All right, so I've written out some steps here, but we're going to talk about these steps through examples, so I'm not going to read through them. You can read through those on your own. Anytime we are solving a quadratic equation, the same rules we had for factoring apply. So anytime I'm looking at something like this, it's easiest to have it set equal to 0, so that's already the case here. And then I want to look for the greatest common factor. So I want to see between these terms, is there anything that they have in common? And in this case, they have a common factor of 2. And then this set of parentheses here, we can see that we have a difference of squares. So I have x plus 5 and x minus 5. And then I can go ahead and use that zero product property, setting each of those equal to 0. If I set x plus 5 equal to 0, then x is going to equal negative 5. If I set x minus 5 equal to 0, adding 5, x will equal positive 5. And this 2 here does not give us an answer. Now, if I had an x on it, if there was a variable attached to this number out front, then it would give us another x value. But being that it's just a constant, I could divide both sides by 2 and the constant would go away. So those are our answers there. Now this next one is not set equal to 0. There's actually two different ways we could go about this one. In the next section, we'll be using the square root method for solving, and that's one method we could use here. Or we could go ahead, like the last problem, set this equal to 0. So subtract 9 and get it on the other side. And then this is a perfect square, and this is a perfect square, and subtraction in the middle. So this is also a difference of perfect squares. This would be 2x plus 3 and 2x minus 3. And if I set both of those equal to 0, and I subtract 3, divide by 2, x is equal to negative 3 over 2. And if I add 3 and divide by 2, then x is equal to 3 over 2. In the next example, it's already set equal to 0, which is nice. And so from there, what we can go ahead and do is try and see if there's a common factor among those two terms. Well, 5 and 10 have a common factor of 5, and both terms have an x. So I can go ahead and pull out an x as well. So 5x is what can be pulled out. And then we're left with x plus 2 equal to 0. And then because there is an x on this constant out front, that does give us an answer as well. So 5x equal to 0 and x plus 2 equal to 0. Here, dividing both sides by 5, 0 divided by 5 is still 0, so x equals 0. And subtracting 2, x equals negative 2. In the next example, it is not set equal to 0 yet, so that's the first thing I want to do is get the 6 over on the other side. 2x squared plus x minus 6 equals 0. And then I can go ahead and, this is a trinomial, I can go ahead and go into the x method. Negative 6 times 2 is negative 12. And then I have my b value is 1. I'm looking for two numbers that multiply to negative 12 and add to 1. 4 and negative 3 multiply to negative 12 and add to positive 1. So 2x plus 4 and 2x minus 3 equal to 0. Taking out the trash here, and I just realized I didn't talk about pulling out the GCF. That's because there was no common factor here, but if there was, I would need to pull it out. And if you're feeling rusty on your X method, you can go back to that video and kind of get a refresher on how to do the X method. So these are my two factors. X plus 2 is going to give me x equals negative 2. 2x minus 3, if I add 3 and divide by 2, x is equal to 3 over 2. Okay. The next one, we have 1, 2, 3, 4 terms. And so when we had 4 terms, the thing we wanted to think about was factoring by grouping. We still want to consider, is their greatest common factor 2x cubed, 3x squared, minus 8x, minus 12. There's nothing that they all have in common. But we can go ahead and go into factoring by grouping. And between these two terms, they have a common factor of x squared, left with 2x plus 3. And between negative 8x minus 12, they have a common factor of negative 4, and left with 2x plus 3. Now these two pieces are the same, so I can go ahead and pull those out. And I'll have 2x plus 3 pulled out. And then what I'm left with is x squared minus 4. Now you might be thinking we're done here, but we're actually not. This factor here is now a difference of perfect squares, so that can be factored further. And what we're trying to do is to get all of our factors with an exponent of 1. And the fact that this says x squared still indicates that maybe we could factor this further. So I get 3 answers this time. 2x plus 3, if I subtract 3, divide by 2, I get x equals negative 3 over 2. X equals negative 2, and x equals positive 2. For the next one, it's going to have an extra step here, and the reason why is because you can see that this is not in descending order. This is what's called descending order. The largest exponent, then the next largest exponent, the next largest exponent, all the way down to the constant. This is not in descending order. So the first thing I recommend is that we get this into descending order. So negative x cubed minus 4x squared plus 9x plus 36 equals 0. And this gets it into descending order here. We can just reorder it like that. And I also notice my leading term has a negative on it. I would rather that be positive. So what I can do is, since we have an equation now, not just an expression, where we were doing factoring by grouping before, I would factor out a negative. Now what I can do is divide both sides of my equation by -1. And what that does is it switches all these signs. So a negative divided by a negative becomes a positive x cubed. Negative 4x squared divided by -1 becomes positive 4x squared. Positive 9x divided by -1 becomes negative 9x, and then negative 36 equals 0. And now we can go into that factoring by grouping. There's no GCF for us to pull out. These have a common factor of x squared, and we're left with x plus 4. These have a common factor of -9 and left with x plus 4. Pulling out those x plus 4s, and we're left with x squared minus 9, and that is also a difference of perfect squares, so that can be factored further. So I have x plus 4, x plus 3, x minus 3 equals to 0. That gives me x equals -4, x equals -3, and x equals +3. We have another one at the bottom of this page, and it is not set equal to 0, so that's the first thing I want to do is subtract 60x over to this side. I have 18x cubed minus 6x squared minus 60x equals 0. And these three terms have a few things in common. They all have a common factor of 6, and they all have an x. So I'm going to pull out 6x, and from pulling that out, I'm left with 3x squared minus x minus 10 equals to 0. And now I can use the x method on that middle part. 3 times -10 is -30, and I have a -1. That's my b value. -6 and 5 multiply to -30 and add to -1. So I have my 6x I'm bringing down, and then I have 3x minus 6, 3x plus 5 equals 0. Here's the trash. 6x, and I have x minus 2 and 3x plus 5. And then we can go ahead and solve for each of those. Since there is a variable on this 6, setting that equal to 0, I get x equals 0. X minus 2 equal to 0, it gives me x equals 2. And setting this one equal to 0, subtracting 5, dividing by 3, x equals -5 over 3. Okay. Couple more on the next page, and then that'll be the end of this video for us. So here I have 6a cubed minus 36a equals -15a squared. Again, I want to get this set equal to 0, so I'm going to add 15a squared to both sides. 6a cubed plus 15a squared minus 36a equals 0. And notice I put that in the correct order here. I have this in descending order. All three of these terms are divisible by 3, and they all have an a. So 3a is what we'll pull out for our GCF. And then we're left with 2a squared plus 5a minus 12. We can go ahead and use the x method. I have -24 up top and 5 on bottom. 8 and -3 multiply to -24 and add to 5. So I have 3a, bringing that down up front, 2a plus 8 and 2a minus 3, 0. Taking out the trash, 3a and a plus 4 and 2a minus 3. You're seeing how important it is that you have those factoring skills down really well, and all these problems will help you practice that even more. So I just set each of these equal to 0 and got all of our a values. one more, and then that'll be the end of this video here. We have 2y times y plus 4 and negative 5 times y plus 3. The first thing I'm going to do is distribute both of these, and then I'm going to get the equation set equal to 0. So distributing here, I have 2y squared plus 8y is equal to negative 5y minus 15. I'm going to get these over onto this side, so I have 2y squared. If I add 5y to both sides, then that becomes plus 13y. If I add 15, then I have plus 15 equals to 0. I can go ahead and use the x method now. There's no common factor among all of these terms. 2 times 15 is 30, and on bottom I have 13. 3 and 10 multiply to 30 and add to 13. So 2y plus 3 and 2y plus 10 is 0. Taking out the trash here, and I have 2y plus 3 and y plus 5 equal to 0. Here I'm going to set that equal to 0, subtracting 3, dividing by 2, y equals negative 3 over 2. And setting this equal to 0, y will equal negative 5. So that is our first set of quadratic equations. In the next video, we will look at a couple more methods for solving quadratic equations, first off by taking the square root.